Hi, and welcome back to Blockchain Fundamentals with Bill Laboon. In this lecture, we're going to start discussing smart contracts. Specifically, we're going to look at the very fundamentals of what makes up a smart contract. And in the next lecture, we will go into depth on building our own smart contracts. However, in this lecture, I really want to focus on the concept of smart contract itself and understanding what's actually happening when you call a smart contract or develop one. But in order really to understand smart contracts, we first have to go back to understand what is a blockchain. Hopefully, since we are now on lecture 19, of the series, you have a basic idea of what a blockchain is. That we have a bunch of blocks that have transactions, and in these transactions, different things can happen. We can send Bitcoin or whatever token of the system to another account. But I want to look at this in a little bit more of an abstract way. So one way to look at the system, a blockchain system, is that we have at any given point in time a particular state of the system. So in the example I had in the previous slide, we had an initial state, let's say, of Alice with 10 Bitcoin, Sue with 10 Bitcoin, Amy with 10 Bitcoin, and Joe with 10 Bitcoin. After this first block executes, Alice gave 1 Bitcoin to Bob, and so Alice has 1 less Bitcoin, and Bob now has 1 Bitcoin where he had 0 before. Sue gives half a Bitcoin to Joe, so we're going to reduce Sue's account by half a Bitcoin, and Joe's is increased by 10.5, and Amy gave 3 Bitcoin to Sue, so she ended up with 12.5 Bitcoin since she gave away half already, and Amy has only 7 Bitcoin. And each block is a way of changing this state. And the only way that the state of the system will be changed is through a valid block. So we call this change a state transition. So we can think of each block as a way of changing the state or causing a state transition. So if we look at the transactions included in each of these blocks, we can see Alice gives Bob 1 Bitcoin, like that's part of the state transition. Now, so we have states and then we have transitions from state to state. But we don't want just any transition to be possible. It's not as though from one state to another, just with the block coming by, that anything can happen. There can't be a Bitcoin block, for instance, that just reverts everybody's balances to 0. Okay, like that's impossible. That is not something that is allowed by the state transition function. So the state transition function is something that accepts a given state and applies a transaction to it, and will either give you some new state of the system S prime, or say it's invalid and we maintain state S. We don't actually make a change. It's just as if you try to issue an invalid Bitcoin transaction. Nothing is going to happen, right? If I try to send a Bitcoin transaction which is not signed, for instance, the nodes are going to look at this. They'll see that this is an invalid transaction. I can't apply the state transition function to it. I just get the exact same thing, so it doesn't make any sense to add it to a block. So just as a really simple state transition function here, obviously in any real blockchain it would be much more complicated than this. We look at the list of we get a group of transactions, and if the transaction amount, what you're sending, is greater than the transaction sender's balance, we're just going to ignore these transactions. We just fail, like this group of transactions is invalid. Otherwise, so that's if in the case that the sender doesn't have enough tokens to actually send. So somebody that has 5 tokens and tries to send 100, for instance. Otherwise, we reduce the amount in the sender's balance by the transaction amount and increase the amount on of the receiver's balance. So here we've got a valid state transition, right? It has gone through the state transition function. It completes successfully. This is just the first transition in the example earlier, where Alice sends Bob 1 Bitcoin. She has that, and Bob can get it. Sue has enough Bitcoin to send, and Amy has enough Bitcoin to send. So again, this is a very simple state transition function. You can imagine it is much more complicated in an actual blockchain. But hopefully this gives you like this concept of what the state transition does and what it checks for. An invalid state transition, here we have Alice trying to send Bob 50 Bitcoin. Alice can't send 50 Bitcoin, so the whole group of transactions we try to send, this just reverts. It ends prematurely. We just say, all right, this can't happen. We're not actually going to produce a block with this, and thus the state stays the same. So another way of thinking of a blockchain in a really abstract way is just repeated state transition function calls, where each block, that's what it's doing. It's applying the state transition function multiple times. So as each block gets added, we start with the genesis state. Then for block 1, we apply any transactions. We can think of the group of transactions as like one big state transition operation and get a new state S1. Then we apply S1 and the new transactions that are found in block 2. We get a new state S2, etc. State 3, state 4, etc. Or if we want to think of this sort of mathematically without these extra variables, we really can think of it as just repeated application of the state transition function. So if you look at the lower example here, you'll notice there are no additional variables. It's just nested calls to this genesis state, this state 0. And we don't need to really have any other additional state. If we know the state and we know all the initial state, and we know all of the transactions that are applied to it, we can get the final state. So again, I'm just saying all of this. Hopefully none of it is too crazy. It's just a different way of looking at what a blockchain is actually doing. So far we've just been changing account balances when we're looking at this in detail. But state can be arbitrarily complex, as well as our state transition function being arbitrarily complex. So here, for instance, we may have a blockchain that handles people's like driving insurance information. So we have Alice, who has a state, an age of 41, valid license is a Boolean, it's true, age is an integer, owns car, that's an identifier. So she owns car indicated by OX9AB3. All right, Bob, meanwhile, is 29. He does not have a valid license, and he does not own a car. He owns, let's say, 0 as sort of the null indicator. But we have a state transition that Bob gets his license. So this, get license Bob. So now we can see the new state after this block. Bob has a valid license. Valid license is true. We have another state transition where Alice has a birthday, so she turns 42. And the reason you'd want to keep track of age is because car insurance companies, they give you different rates based on your age. So she's now 42. Maybe that means she has a lower rate. Whereas Bob buys a car, which is identified by OX11E3. So now Bob has a car. So we're changing the state in more complicated ways. You can imagine get license and buy car. All of these individual functions that are being called by the state transition function have more or less complicated logic. Birthday is probably pretty simple. It's just increment age of that user. Alice.age plus equals 1. Whereas by car may have a whole bunch of checks for identity to make sure that Bob actually owns the car, etc. But it's still just a state transition function. There's still just some the state has changed somehow. So this can be built directly into the software of the node. So we often will call this is the runtime. This is like what the blockchain itself has as its state transition. Or we can make a sufficiently abstract state transition function that code itself can run on top of it. So your state transition function may be like you'll run this additional code. And developers can then write and deploy their own code to the network. And this is what a smart contract is. So if you think about it, in some sense, Bitcoin actually is capable of running very limited smart contracts, since Bitcoin transactions actually run, you remember Bitcoin script, which is a stack-based language. It's very, very limited, though, in what you can do and in what nodes will actually accept as your script. So there's not a lot you can do here, but you can issue transactions on Bitcoin that have slightly more complicated capabilities than simple just transfer of value. But there are still it's limitations to this. It's very difficult. There's not a lot of possibility to support additional data types or functionality, and most importantly, it's not Turing complete. So a Turing complete language is a language that's capable of computing anything that any other computer can. So there's an equivalence between them. So any Turing complete language can compute anything that some other Turing complete language can. Now, this doesn't mean that it will be able to compute it easily, or will be very quick to write, or efficient, or readable, anything like that, just that it's possible. And there are a lot of languages out there that are Turing complete. Most programming languages that you may be familiar with are Turing complete. However, there are many also that are not. Bitcoin script, as I mentioned, is deliberately not Turing complete, and this limits what we can do with it. But a Turing complete language, no matter again how it looks like, will be able to compute the same things. So here I want to compute how much 3 times x is, and print it out in reverse order from 1 to 10. So print out what 10 times 3 is, then 9 times 3, and then 8 times 3, all the way down to 1 times 3. So to get the output that's at the top right there in the cool hacker font with black and green. So I could write that in Haskell as map 3 times $reverse 1 ... 10. Okay? Or I could do this in Ruby, 1 ... 10, change to array, reverse, map with the function x 3 times x. Or in Java, import Java util arrays, public class build, public static void main, ... Okay? All of these will do the exact same thing. And anything that I could do in Haskell, I could do in Ruby, I could do in Java. Okay? This is not the case for something like Bitcoin script, okay, which really limits us on what we can do in terms of smart contracts. So there are some benefits and drawbacks to having a Turing complete language. The big benefit, as I already mentioned, is that you can compute anything that any computer can compute. Sounds like Dr. Seuss or something. So the big benefit, you can do whatever you want. But the drawback is you can compute anything. It's impossible to predict perfectly what is going to happen without actually executing it to predict this in all cases. So this means that it's going to be much less secure. There's a lot more things that you have to worry about. There's a lot more analysis you can do and a lot more restrictions on a non-Turing complete language. But it really limits what kind of state transition functions we can create. So again, just like anything in software, there are trade-offs. Turing completeness is not an unmitigated good, but it's also not an unmitigated bad. So let's talk about an implementation of these of smart contracts using a Turing complete language. So although the idea of smart contracts actually goes quite a while back into the 90s, Nick Szabo, The first really major implementation was Ethereum, which really started to be produced, to come out in 2014. So Ethereum is a blockchain that has an Ethereum virtual machine, the EVM, and users are going to write in a high-level language. Nowadays, it's almost always a language called Solidity, but there's also LLL, Viper, Serpent, which is now deprecated, but was in the early days seen a bit. And this compiles down to EVM bytecode. And the state transition function of Ethereum allows you to run this EVM bytecode. You can call into different functions. So remember, though, that smart contracts are executed on every full Ethereum node. If you are going to run some code, every single Ethereum node in the world is going to run that. That's just how blockchains work, at least non-sharded blockchains. So that means that your computing power is actually very limited. The joke is it has as much power as a 90s cell phone. Okay? So generally, with these smart contracts, you're only going to put like a very small amount of the full code of whatever application you're going to put in. Only that is just really necessary. And then GUIs or any non-relevant information or data that can be computed from that data is going to be put elsewhere. We also, since these smart contracts are run just like a program, they're immutable because they're on the blockchain. They are up on the network, and they do exactly what you tell them to do, no more, no less. So there's very much the opportunity for bugs in a smart contract. And when this happens, bad things can happen. If code is law, if what we execute is law and there's a bug in the code, the program doesn't know that there's a bug. So unlike a contract that may have a typo, like a real life contract, that may have a typo, but people realize that I would give you 10 turtles, but the contract says that the owner will give you 10 tuttles. In real life, people will realize, okay, they actually meant turtles, but in a smart contract, no, you're getting the 10 tuttles. So figure out what a tuttle is, because you're getting 10 of them. So before smart contracts are deployed, they should really be well understood, well designed, well audited before you use them. There are a lot of different possibilities for things to go wrong with a smart contract, and we've actually seen quite a few in history. There have been a lot of bugs that have been exploited in smart contracts. And since at least the bytecode is open source in most blockchains and Ethereum, because you're deploying it and others have to actually execute the smart code, there are potential exploiters, people that are looking for vulnerabilities everywhere. You can't hide hide the code that you're executing generally. So I just wanted to give an example of a smart contract. This is written in Solidity, which is what we will cover in the next lecture. So here I have taken this from Open Zeppelin, their ERC20 Solidity, one of their functions, which transfers from a sender to a recipient. So you can see that we check that if we're not trying to transfer to or from the 0 address, we're going to do everything that has to happen before a token transfer. Then we subtract the balances. The before token transfer includes checks. Some of the checks, like what I discussed in our simple state transition function earlier. Then we are going to subtract the amount from the sender and add it to the recipient and emit an event saying that a transfer took place. So if you're a programmer, none of this code should look too strange. It's maybe you don't understand all of the keywords, but it should be followable. But remember, this does get compiled down to EVM bytecode, just like Java code gets compiled down to JVM bytecode. But if you're a programmer and you know that this is Turing complete, then you may think, well, what happens if I do something like this, right? I have an infinite loop where just, while a equals 1, b equals b plus a, I never actually update a, so a will always be equal to 1. So does this mean that every node is going to be stuck forever, just constantly running this infinite loop? And the answer is no. There is a solution to this. And that solution is something called gas. So every EVM operation, every computation that you do is paid for by gas. And when you call a transaction, you also state, here is how much I would like to pay for gas with Ether, and here is the maximum amount that I will spend. So if a call runs out of gas during execution, then the state reverts. Nothing happens, but the Ether still was used to buy that gas. So you were able to run this, at least for a while, but nothing happened. The state stays at state S. It never moves to state S prime. Everything just reverts. But you wasted Ether by buying that gas. So this really mitigates against somebody trying to use a smart contract as a sort of like denial of service attack. And it also ensures that people are very wary of doing too much actually on blockchain, actually on the smart contract, because it's going to cost them money. Since there's only a limited supply of space on each block, we really want to have people minimize how much code they actually want to run on the blockchain. There's only a finite amount of computation that people can do. There's only a finite amount of storage that can occur on a blockchain. And so gas really helps us to prevent this sort of thing. And computations that take up more computation, right, are going to take up more gas. And since every bit of storage has to go on every single node that's running this, storage also is very expensive in terms of gas. So gas allows us really to this concept of gas, or other blockchains call it weight, or there are other terms, but this idea that you're going to have to pay for the computation that you do really is what allows smart contracts to exist on a shared blockchain. So hopefully this has given you a good idea of how smart contracts work. In the next lecture, we're going to actually walk through creating our own smart contract.